Okay, so this is what I consider to be a collapse of the wave function, because notice there's no divergence or convergence. And what I mean by that is, here I've got, let me go to another value. Now see that I've got divergence, and I've only graphed 1/4. I could have graphed the other 3/4, but and it goes out to infinity. So you've got divergence of the red, and or I could give another, just shove something in, and there I've got divergence of the blue ones. And in the case of the blue ones, that is going to be L squared, and then it drops back to L, then back up to L squared, and then L squared, then L, then L squared, then L, then L squared, and that's how it goes around and around. So I'm going to show that the wave function is L, which is the probability amplitude, and when you square that you get the probability density, which is L squared. So I'm thinking that I want to replace waves with these diverging and converging relativistic slide rule, and then it will all disappear when the wave function collapses here. So you can see here that I've still graphed, I've still got it on divergence and convergence. You can see there's still a bit of stuff there, but it's not diverging or converging. So it's like the wave function has just disappeared, and I've got a measurement here which is 100%. This would be Alice's classical reality, which is her measurement, 100% to the right, and then on the other side I've got Bob's classical reality, which is 100% to the left, and that's because of conservation of momentum. So I want to show that the distance between Bob's measurement and Alice's measurement, let's say they're entangled particles, that distance between is this. You know, see it shows 100%. Its length is 1 at the moment. You square it, you get 100% probability. Okay. Now let's say that they've each got a single wave function, and they're going to measure at a 45-degree angle. Just get rid of that. So okay, so here's Alice's measurement, and now the probability of her measurement being successful is going to be 85%, and you can see that's the 85%, and the probability of Bob's measurement being successful will also be 85%. So here I've shown their B values separately. So this is like they got separate wave functions, but notice that they're actually sharing a length between, which is the distance between both measurements, and they're sharing that. And when you square it, you get the probability of their measurements being successful. And because it's special relativity, you can't say who did the measurement first, because they're not together. So in the middle here, you could say that they're in the same place and time, but out here, they're not in the same place, so you can't say they're at the same time. And it turns out that if I combine their two separate wave functions, which is the relativistic slide rule, if I combine those two relativistic slide rules into one relativistic slide rule here, then I can calculate the combined probability of them being successful with that measurement. So I've got that backwards. That's the combined wave function there, and that's their separate wave functions here. So separately, they can still correctly calculate the probability of their measurement being successful by just continuing to graph their separate relativistic slide rules, and in that case, L is the wave function. You square the wave function, you get the probability, which is 85% of success, and they can both separately make that measurement by seeing where it crosses over here. In other words, it's L squared, or 1 minus B squared, depending on how you want to look at it. It's normalized, but I can combine those two into a single capital B combined wave function, and that's the calculation there. And now I end up with just a single 2LB, which is actually equivalent to their separate L's. But the reason I'm doing that is because that is actually magnetic flux, 2 times the magnetic flux. So on the relativistic slide rule, that's magnetic flux, and that's magnetic flux. So there's 2 of them, and then you square them. The SI unit is Weber. Okay, so that's how the information is transferred simultaneously, like a superconductor, zero resistance from there, straight across. Okay, so they share the same probability of success, and then when they make the measurement successfully, it collapses to here, and the waves which guided the entangled particles, they disappear, because that goes to 0, boom, and I've actually graphed the square of that magnetic, 2 times the magnetic flux, and so that length is 1, and that's transmitted. Cool. I'll have to get out of here now. Okay, let's get out of there. Let's have a look at this. Okay, so here I've they've both made a measurement on a 45-degree angle, according to them. This is relativity, so they're on different lines of simultaneity. Okay, and their measurements have a probability of 85% success, being successful. and if they're successful, then it collapses to the 100% here. So you can see it all depends on that length squared, which is that. So that's L and that's B. Multiply them together, you get that length, and then 2 times that length to get the total distance between their calculations, between their measurements, I mean. Alternatively, they can separately have separate wave functions, in which case they would have separate relativistic slide rules, and you simply square their little b values. I mean, no, you don't. 1 minus the little b value squared, which is just little l squared. It's basically the length from there to there. And in this case, it's 0.85, so 85% in both cases. And then it collapses, and that is actually maximum information entropy. So there's an increase in entropy when there's a measurement, and there's a disappearance of the waves, that guiding waves. And so all of these calculations in here are within the quantum realm. So this is quantum mechanics inside, and outside is the classical realm. So that's just classical mechanics. And outside you've got this is the B field, this is the electric field, the magnetic field. There's H, there's capital M. Add them together, you get the magnetic density. And then also you've got outside quantum mechanics, you've got capital T and space-time, which is LT. And we know all about that, but we don't know what's going on inside this quantum realm, and so that's what I'm trying to calculate. And I have to give the reason for the instantaneous knowledge as to what the other one's measurements was. They have to be both 85. They have to both have this exactly the same probability. So you can see the probability of success goes to 0 there, and it goes to 100% here, down here. Goes to what else? What else have we got? Yeah, so just looking at these wave functions interfering with each other, I've just tried to do a bit of a thing. So as I was saying, this is just a rough idea that before collapse you have diverging fields, you can see. And as I was saying, as you go round, you go L squared L, L squared L, L squared L, L squared L. So as you go round, it's always like that. So it's like you've got some sort of wave function like that. And then here it could interfere. Say this is another slit, there's a slit, so you could have interference. This is just a rough idea. And where they cross, you get constructive interference. So here's the screen. This is the transmitted photons detected. They were transmitted, and I showed the calculation for transmitted. It's actually density, intensity. And I showed that with refraction. I was showing how you get transmission, and the calculation I showed it was in fact that. For intensity, so maybe this is where they've gone wrong. They haven't got the correct dimensional analysis for intensity. And that's collapsed, and there's no waves anymore.